If your car gets stuck in a mucky patch because of which, say, one of its wheels starts slipping and the car is not moving ahead. In this scenario, you can see the wheel with the least traction starts slipping and the vehicle goes nowhere. One option to solve this is by shifting to 4-wheel drive mode. However, there is another option before you do the ultimate shift, which is locking the differentials.
Introducing the Eaton Mechanical Locking Differential. At the heart of the Eaton Mechanical Locking Differential is a beveled gear set, similar to the ones in the conventional open differentials. There are 2 pinions located on the cross shaft and 2 side gears splined to the axle shafts. These gears are precision forged for high impact strength. One of the side gears has cam ramps machined on the back face of the gear. These ramps mate to corresponding ramps on the cam plate. Also, there are 3 detent protrusions on the cam plate, which make 2 holes on the side gear. The detent system prevents the cam plate from ramping until a predetermined torque is applied to the gear teeth. When the cam plate rotates out of the detent, the ramp surface on the cam plate engages the ramp surface on the side gear. As the cam rotates further, the ramps cause the cam plate to move in an axial direction. The ramps are symmetrical, so the same action occurs in both directions of rotation. Behind the cam plate is the active disc pack, and behind the cam plate hub is a wave spring designed to keep the cam plate in the detent position. Following the active disc pack are more friction discs, a snap ring and ear guide clips, designed to maintain disc gear alignment during assembly. On the other end of the differential is another set of friction discs that reside on the opposite side gear. This disc pack develops torque from the force created by the cam gear and then transferred through the reaction block located in the center of the differential. The device that activates the cam plate is the engagement mechanism. The engagement mechanism is connected to the cam plate by a shaft that is geared to the cam plate. The mechanism is attached to the shaft through cone clutches and an end plate on each side. The mechanism can rotate relative to the shaft when the torque between the shaft and the mechanism is greater than the cone clutch torque. The mechanism is made up of 2 flyweights that are spring-loaded toward the center of the shaft. The shaft rotates whenever there is a difference in the speed between the wheels. When the differential speed reaches approximately 100 RPMs, there is enough centrifugal force on the flyweights to overcome the centering spring. The flyweights move outward to catch the claw of the lockout mechanism. There is 1 claw for each direction of rotation on the engagement mechanism. If the vehicle is travelling over 20 miles per hour, the centrifugal force acting on the counterweight of the lockout mechanism will cause the engagement claws to rotate away from the engagement mechanism. When this happens, the differential cannot lock up at high speeds. With the parts back together, it can be seen how all the parts work to cause lockup. With 1 wheel spinning, the cam side gear rotates relative to the case, causing the engagement mechanism to rotate at a higher speed. At a given speed, the flyweights will swing out and engage the claw on the lockout mechanism. This action creates a force to be exerted on the cam plate, allowing it to rotate out of the detent and into the ramping position. The active friction disc engages, causing the cam ramps to self-energize, until enough torque is developed between the wheels, allowing them to lock together. With the wheels locked together, maximum driveline torque is available to the high traction wheel. And because it's automatic, the traction is available when you need it. This self-engaging diff lock is so much better than manually switched lockers, as it's available when you need it, not after you've realised you need it.